Good morning. Hello. Good morning. Nate, how are you? Are you there, Nate?
He's still connecting the audio.
Are you there? Nate, is that you? Nate, are you there? Hello. Nate. Hello, hello, hello. Can you guys see the problem in the back? Okay, no worries. All right, everybody listen. Don't log on and then leave the computer just sitting there, just so, you know, because sometimes at the end, there are some of you whose names are there and I'm trying to check out and you're not responding to me. I'm guessing it's because you're away from your computer. So please don't do that if you can help it. Couple minutes to go. Go ahead and look at that problem and try to understand what's going on. Hi.
Hello.
Hello. How are you?
Good, how are you?
Good. Get to the chopper. You guys are almost done. I mean, I could, if I wanted to, I could finish the whole course today, but I'm not. I'm going to do some extra stuff before we move on to the last section.
What lesson are we on?
12.5. Last lesson of our traditional course is 12.6, and then everything else is extra that I'm adding on. Algebra 2, combinatorics, other stuff, auxiliary stuff. So you will be done with the course of geometry material after 12.6. And then, of course, we have to review and then take the test on it, which is an opportunity to improve your grade. All right, 8:30, here we go. All right, folks, so good morning. And, oh, let me close this door over here. How embarrassing. Just kidding. It's just the bathroom. All right, so when you make a call on a cell phone tower, or you don't make a call on a cell phone tower. When you make a call on a cell phone, let's say that you're traveling on a map somewhere within the red circle. That means you're within the coverage range of tower B. If you travel outside that range, you're not communicating with that tower. All right, so you would be out of range. You could lose your call. But now, if you have enough cell phone towers with overlap, by leaving one zone, you're traveling into some other zone to some other tower. Okay, so that's why you need these overlapping circles here to do that. All right, now a tower that if you notice the radius, the coverage zones could be different, right? So you don't get as much coverage, you don't get as big of a coverage zone from tower A. All right, so when in the diagram, the centers of these circles, O and A, are locations of cell phone towers, and also B. So for A, what is the equation that models the position and range of tower A? So we're going to need an equation for that. I'll do that in blue since that's written in blue. So we want the equation of that circle. So what makes up the circle is going to be the center point, that's the reference point, and then the radius. Okay, so the center of that tower, now careful, it counts by twos, 2, 4, 6, 8, 10, 12. And this is 2, 4. 12, 4 is the center of that. All right, and then the radius of that circle is 2, 4, 6. All right, so now we do our equation. All right, and if you remember from yesterday, it's x minus the x coordinate from the center squared. And as I'm building this, you should try to understand, here's some central point, right? And here's some radius drawn to the circle, which has an xy coordinate on it, right? And what you're figuring is the Pythagorean theorem is what we're building here. Delta x, delta y, a squared plus b squared equals c squared, right? Which is your radius. So what you've seen here is a delta, the difference of the x's between the center and that some random point on the circle, right? And you're saying it's diagonal, but we break it into two components. That's what we do with vectors. So this helps you understand vectors as well. We're breaking, instead of going diagonally, we're going in pieces. We're going horizontally, and then we're going vertically. Horizontally, that distance is measured by thinking of it as a change in location from here to here, delta x. Okay, I'm giving you a full review. Okay, so then that's why you see a minus there. It's this x minus this x gives you the delta, the change in x. And then that's a distance, which is like a, the length of the side of a triangle. So a squared plus b squared equals c squared is going to be how the circle is related as an equation. Okay, so that's what you're picturing as we're building this. So it explains, so you're not just doing it as a memorization. As I'm writing this, I'm realizing what I'm doing here is, oh, this is delta x. And that's the side of a triangle, a squared. Now my plus my b squared, that's what justifies me putting a plus there. Delta y. The coordinate on the circle could be any coordinate, y coordinate of the circle. And how far is that from the y coordinate of the center? That's my delta y. And that's just the vertical length of that side of that leg of the triangle, the vertical leg of the right triangle. So that's a b squared. That justifies the squared. Equals c squared, the hypotenuse, which is the radius, squared. 6 squared is 36. Done. Got it? That was more of a performance than kind of performing that. Oh, you're sticking your tongue out at me. I get it. I get it. All right. Same thing for B. Any questions about the equation for circle A? Hello? No?
No.
No. Okay. Circle O. Oh, no, this one wants B. What is the equation that models the position and range of tower B? So we'll do that one in red. I left my red marker in San Francisco. You guys get that reference? I left my heart in San Francisco. Never mind. Okay, so the center of tower B I could put just point B. That's kind of how it's labeled. Go back. This one was A. Let's see, 4, 12. Radius, 2, 4, 6, 8. Okay, so it's a bigger coverage zone. All right, so here we go. Now that I've done this and I understand how it works, it's actually quick. X minus 4 is delta x squared plus delta y squared is equal to the radius squared. It seems like it takes a long time when I'm sitting there explaining the deeper parts of it, but actually once you get it, it's just boom, 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 boom. Okay. Questions about that? All right. What about tower O? That's centered at 0, 0. Okay, so tower O is at 0, 0, centered. And the radius is 2, 4, 6, 8. So you'll have x squared plus y squared equals 64. You're subtracting 0, right? So that's what it looks like. Any questions? No?
0 parentheses 0 comma 0 parentheses.
What was that? Oh, this here?
Yeah,
It's an O. That's an O.
I know.
I know you know. You're just venting your frustration at the naming, at the nomenclature. Okay, no questions. Okay, great. Now I want to add something that's not in the slides. I want to talk about earthquakes and
Triangulation.
okay, please don't give stuff away. All right. So, how does a seismograph work? There's an earthquake that sends out S and P waves. Okay, so it's boom from the epicenter, right? Moving out, moving out, moving out, moving out, like waves coming out, like you drop something in a pond, right? In all directions. All right. So how do we know where the earthquake came from? Okay, so we have to locate some epicenter. So if we have a seismograph right there, and it knows how the difference, you learned this in 6th grade, the distance between when the P wave and the S wave hit the seismograph, the longer it, the further away, the further the distance is between when the waves are detected. All right, so we know how far away the earthquake is by that, but you don't know in what direction. So once you have a seismograph and it picks up an earthquake, it could be anywhere in that radius, in a circle. So the earthquake could be anywhere on the blue circle, but you don't know where it's located. So we build another seismograph. And that is also going to pick up the earthquake in a certain radius. Let's say that this one, and we've now narrowed it down. If the earthquake must be the purple distance away from here and the blue distance away from there, the earthquake could be in one of two locations. It has to be either there or there, so you've greatly narrowed it down, but you do not know for sure which location was the epicenter. That suggests that it requires minimum how many seismographs to detect an earthquake?
2.
3.
No, not detect whether there was an earthquake, but to detect where the epicenter is located. 3, and what David says, this has a name, it's called triangulation. So that means that there's some other seismograph located here that picks it up. Now we know for sure it's not that location, it's that location. Okay? But what is that point mathematically called?
The focus.
No?
The solution of all 3 circles.
Yes, it's the solution to the system of 3 different circular equations. Is that possible? Do you have enough knowledge to find the solution to a system of equations of circles? Yay or nay?
Yay.
Yay.
Yay? Okay, you say so? Then let's go back up to our other one and let's look at the first two, A and B. Let's go and look at A and B. I want to see, now here's the extension for you guys that could take up a good 10 minutes here. I want to see you guys work on where these locations are. Where does, now we're not going to do the full one. We're not going to do A, B, and O. All right. But what I want you to do is I want you to find the solution to the system of equations for A, circle A, and circle B. Try to do it the best you can right now. It's a very tough task, but try it. Use your calculator. Okay, you're going to need to write those equations, and we already have them in your notes, hopefully. Let's put back up the equation for A. There's the equation for A and the equation for B. I know some of you are going to get stuck right at the beginning. Hey, Jack. Jack picked garlic from our yard, and he hung it up in his bedroom for vampires. He didn't want any vampires to come into his room.
No, the windows is closed. I wanted to give it to you for a present.
Thank you, Jack. I appreciate that. No, that's okay. I'll hang it from the door. Oh, it smells like garlic too. There we go. All right, so the equation for the second one is, so the coordinate is 4, so x minus 4. The height is up at 12, so y minus 12. Oh, it's a reverse of the other one. But the radius is different. The radius is 8, so there's the radius squared. So some people are going to get stuck right at the beginning of this. Oh, you know what? What might have been better, easier to do? You know what? Let's back up. You want to make this easier on you? We could give you circle O. Might be easier to do. Let's do circle O. Do you guys want to back up and do circle O instead? Because it's x squared plus y squared equals 64. Yes? No? Maybe so?
Yes.
Yes.
Yes? Okay. Let's do circle A and circle O, the black one. Black and blue. So this one is x squared plus y squared equals 64. Okay, let's do that one instead. That'll make this one easier for you. So then you're finding where that is. No. You're finding where that black and blue, that point, and you're finding this point. This is not drawn to scale. So it may not meet right where you see it. It's going to be close. Make sure when you get an answer, if you're able to get an answer, make sure it's reasonable. It's in a reasonable location. Okay, and I know some of you might be stuck. So the first thing I'm going to tell you to do is to expand this blue one. X squared minus what?
144?
No.
Minus 24x.
There's a middle term. If you keep forgetting that, you need to do this. X times x. X times negative 12. That's what you're leaving that out. Negative 12 times x. Then you have negative 12 times negative 12 is positive 144. Okay, see? 4 terms, right? A binomial times a binomial. 2 terms times 2 terms is 4 terms. Okay? And then
You can simplify it.
And then the 2 in the middle become negative 24x plus 144. So you got to remember what you do here. This one squared minus 2 times the product of 12 and x.
Perfect square.
Plus negative 12 squared. And that's what you're going to get here. Okay, so hopefully all of you know how to do this quickly without error. This needs to happen quickly, especially going into Algebra 2. You need to be able to do this squaring of a binomial very quickly. Okay, so the blue one turns out to be x squared minus 24x plus 144 plus, what about this one? Y squared minus 8y, because of 4y times, you double it, it's 8y, plus 16 equals 36. Okay, that looks like a mess, and some of you start saying, am I going to go forward with this or not? You just go as far as you can. Keep going, play around with it. The blue and the black have to interact at some point. It's not ready to interact with it. What if the left-hand side of the blue looks like the left-hand side of the black? See that? If the left-hand side of the blue says x squared plus y squared, and the black one on the left says x squared plus y squared, use the transitive property, then the right will equal the right. So let's simplify that down. Okay, so what do we have here? X squared doesn't have any partners. Negative 24x does not have any partners. Okay, 144 and 16 make 160, right? So I'm going to subtract the 160 on both sides. What am I going to get? Negative 124. Then I'll have okay. Let's add the 24x and the 8y onto the other side, leaving you just x squared plus y squared. So then I'll have 24x positive on the other side, positive 8y on the other side, minus 124. Aha. Now this and this look the same. Okay, we're going to bring this down a bit. Okay, that means 64 is equal to this. Okay, so 64 is equal to 24x plus 8y minus 124. Okay, what are you going to do now?
Add 124.
Add 124, okay. 24x plus 8y is equal to, add 124, you get 188. Maybe you want to divide everything by 4. Divide everything by 4, you get 6x plus 2y is equal to 47. What are you going to do with that?
That looks like a standard form of an equation.
It sure does. But what are you going to do with that? How are you going to solve the system with that? Any ideas?
You need another.
Two equations with two unknowns should have done it.
What happened to the plus 16 equals 36?
Plus 16 equals 36. Where's that?
In
here?
the top. Mm-hmm.
I put these together to make 160. Then I subtracted 160 on both sides to get the negative 124.
Rosenthal, maybe what you did wrong is that you made it kind of like the x squared plus y squared act as if it's the whole unknown. I don't know if that matters, because that's the thing that you substituted. Normally it's a single variable.
Well, is it true that this x squared plus y squared is equal to that?
Yes.
Yeah.
And that x squared plus y squared is equal to that. And the x and y are the same x and y in those two locations. So that has to be true. So this has to be true. Okay. So where would you go from there? How would you figure that out? Could you solve for x or y here and plug it in?
Can you make it
Yes.
equal to 0?
Why don't we do that? Why don't we solve for y, and then we can plug it into the 2y right here. And then we would just have, we would have an x squared component in there. Okay, but it would all be in terms of x. We might be able to solve it from there with a quadratic, which will be a plus or minus situation. And with a plus or minus situation, we're going to get 2 answers, which is what we want. We want 2 solutions. So why don't we do that? Let's solve for y up here. So this would be y squared is equal to 64 minus x squared. Oops. By the way, that's a difference of squares. Put that back on. You're going to need to take the square root of both sides. Okay, so if I take the square root of both sides, you're going to get this. Am I going to be able to plug that in and solve that there?
Yes.
Okay. So let's go down lower and see how that turns out. 6x plus 2 times whatever y is equal to 47. Okay. Now what am I going to do? Get this all to the other side before I square everything? Okay, square both sides. That becomes a 4 when I square it. And then when I square this, I get rid of the square root.
No, but wouldn't it be like 2 times 2?
You would square this, so you
Uh,
square this, and you square this. So that gets rid of the square root. Over here, you have a binomial that you have to square, right? So you're going to square the first one. You're going to get 36x squared. Okay. You're going to combine these and double. So let's do 47 times 6. Let's see, 240, 282. Negative 282, and then you got to double that, 564. X. So what I'm showing you here is we don't shy away from it. None of the work that I'm doing is beyond your skills. You're just not used to going here and doing these things, but if you're having trouble, it's because it exposes some of your misunderstandings about algebra that you're rusty on, or that you never understood the first time. So what's 47 squared? We'll have to do that. 47 squared, 2209. Okay, this is looking better. Now, if we get everything to the right-hand side, then you'll have just a quadratic that we can solve, right? Okay, so what we could do is we could distribute this and then get everything over. So this is 256 minus 4x squared. And then I'm going to get those over to the other side. So I'm going to add 4x squared, which should make this over here 40x squared. All right, minus 564x. Okay, and then I'm going to subtract 256 from 2209. 1953. Okay, and that's equal to 0. All right, now we have something that we can plug into the quadratic formula. Okay, so let's start doing that. I know this is tough for some of you. I hope you're not checking out. It is, as we finish this geometry course, this is really good to practice this, and we're applying it to our circles, right? Just to show you that you can do this. All right? All right, so here we go.
Strauss, that was the original problem, solving a system of equations where the 2 equations were circle equations?
Yes, exactly.
Oh, okay.
Okay, so I'm going to try to find a little patch over here to work this out. So negative x is equal to, in this situation, the x coordinate, it doesn't give you the both coordinates, the x coordinate is going to be equal to negative b Okay, b is negative 564, so it'll be negative negative, so it'll be positive 564, plus or minus the square root of b squared, so it'll be negative 564 squared, minus 4, a is 40, c is 1953. All over 2a, which is 80. All right, so we can start working that down now. So that'll be 160 times 19. So here we go. 564 squared, 318,096. Minus, I'm going to put parentheses on here. Let's see, that'll be 160 times 1953. Close parentheses, equals. Okay, so that's 5,616 is what I got in here. Did you guys get the same thing here? This is called the discriminant, right? Remember that, the discriminant? Okay.
Yes.
All right, so I got 5616 in here, and then you take the square root of that. I got 74.94. So now I have 564 plus or minus, we can even round it if we want, to 75. Just for right now, plus or minus 75 over 80. Those are my two x answers. Okay, so I want to record both of those. X could equal one thing, and then underneath x could equal the other thing. I'm going to do them separately because I'm going to plug in one of the x's to get a y that goes with that x, and that will be one of the intersections. And then I'll go start again with the other x and plug that in to get the y that goes with that. And then last, I have to see if it's reasonable. It could be that I made some calculation error here and that my answer is unreasonable, and then I would have to start over. I'm not going to start over this time because this is correct, what we're doing, although we could have made a calculation error. But let's see if our answer is reasonable. It could be reasonable and you still made a calculation error, and you're just close, but not exact. Okay, and I rounded. Okay, here we go. I guess I'll leave this in my calculator, what I have here. Plus 564 divided by 80. I got, that can't be right. So let me do that again. 564 plus 75, 639 divided by 80. I got 7.98, 7.99, so about 8. I'm going to round that to 8. Okay, and then I got 564 minus 75.
I believe that's 489, isn't it?
Divided by 80, 6.1. Okay, I think that's right. I think I remember getting the 6.1 because I've done this. I did this the other day, last week. That's what made me want to do this for you guys. Okay, so let's plug it in. What would be the easiest case to plug this in? Maybe right here? Up here, maybe? Unless you guys see a better spot for plugging it in. Could plug it in here with this linear equation down here. Okay, I guess it doesn't matter. So let's do it here. Okay, if x is 8 and you square it, you're going to get 64. You're going to get 0 for y, which is close because if we look back up here, well, I don't know why that came back on here. I think that might actually be reasonable. What happened over here? Oh, we want that full screen. Okay. 8, 0. You see how I got the 0? Plug 8 in. 8 squared is 64. Subtract it, and you get y squared equals 0. So y would have to be 0. Let's look at 8, 0. Oh, look at that. Now, because we rounded, it doesn't actually meet right at 0, but it meets pretty darn close. That is definitely a reasonable answer.
Oh, we cannot see the board, Mr. Rosenthal.
Oh, sorry about that. I'm pointing at all this. Look over here. There's 8, 0 right there. And look, so we found that point of intersection right there. About. It's not exactly 0, and it's not exactly 8, but that's a reasonable answer. Now I realize what we're going to do when we find the other one. Okay, when x is 6.1, let's go ahead and square that.
Square root of 26.79.
So I'm going to actually leave the more accurate one in my calculator. Okay, so then I'm going to subtract that from 64. And then I'm going to take the square root to find y. Okay, 5.2. (6.1), 5.2. Let's check that out up here. 6.1 is about here. 5.2. There it is, right?
That's almost exact.
Great. Yeah, that's it. It worked out, folks. I'm so happy. All right, so let's examine what we did again. We wrote out the equations of the circles, right? There's the cell phone tower A, cell phone tower O, okay? We then expanded this one. So that happened here. Okay, so that's the binomial.
X squared plus y squared.
With the binomial expansion here is we binomial times itself. That's what the squaring does, gives you these three. This one squared gives you those three. And then, of course, we had the radius squared over here, Pythagorean theorem. We put the constants together and subtracted them.
Can I see the third circle?
The third circle? Circle B? Are you working now? Okay,
Yeah.
so you're going to work on those. What you could do. What are you trying to find when you do that? A triangulation?
Yeah.
Okay, so you know it would be here. It would be at 6.1, 5.2. If you plug 6.1 and 5.2 in, that's if these were triangulated. But in the cell phone example, this is not necessarily meeting where the other ones meet. See what I'm saying?
Mm-hmm.
This could have gone through this overlap part, the red one. So you're making an assumption that they all met right there. It's not the seismograph problem, where that's backwards, right? Here, these are emitting outward. In the seismograph, there was a point already emitting out to the seismographs, which is how you knew it was coming from a single point, right? So it's like a reverse thing. So you don't know that this coverage range is going to go right out to that same, they're all going to meet at that point. You don't know that.
Mr. Rosenthal, if you had three equations for two variables, wouldn't that be an excess?
Yes. Yes.
But you could still
it could be helpful.
You could still triangulate with three equations though, right?
Yes.
Oh.
Yes, with three equations you can triangulate if there is one point, one source, like the earthquake epicenter. Here there are three sources emitting out, right? And your cell phone is communicating back and forth with that. I guess if you're the source, let's say you're here, then, but this is not the coverage range then. This is just the cell phone tower reading your distance from it, which is not, I don't think that's what it does. Maybe it does that. I don't know if it can do that or not. But this is the coverage zone of that tower. So this is, think of that as a range from that point. Triangulation was the earthquake happened at a point, and the waves went out from that, and these picked that out.
Let's just say one cell phone tower let's just say all three cell phone towers detect the point and you want to know the coordinates. If you use three equations, you'd be able to pinpoint it down to that one point, right?
Yeah,
that's the point where they all.
That's how the GPS. That's probably how the GPS is working it, right? Through a triangulation.
I believe so. Although I believe
It uses it through triangulation using satellites.
Although
At any given time, there's three satellites above your head, above you in the sky that can triangulate your position.
Yep.
Although, Zygmunt, I believe that sometimes it would be better measured to use more than three sources, as within seismographic triangulation. They often use four or five or more seismographs in order to locate the origin, the hypocenter of a single earthquake.
And you're saying it gives more accuracy, is what you're saying?
Yes.
And also, in case one of them is damaged, you can notice that if there are three, then it doesn't really work like that.
Mm-hmm.
If there are four, you can double check.
Mm-hmm.
Yes, that's also.
Okay, let me get back to the recap of this. So we expanded this one, expanded this binomial. We got the constants together. and subtracted them from the 36. Okay, so this was 144 and 16 was 160. Subtract that, you get this negative. Okay, we then thought, well, if I can get the left side to look like the black one, then I can use transitive property. All right, so then what I did is I got the minus 24x to the other side. I made that positive. The minus 8y positive on the other side of the equal sign. Okay, and then I was able to say that this right side was equal to this right side. That's what you're seeing here. Okay, then what I did is I got the constant over. I added 124 to the 64, gave you the 188.
Can you bring the camera down, please?
Oh, yeah, sorry. Okay, and I will kneel down here. Okay, so then we were, let's see, where were we? Here I added the 124. See, I'm recapping. This helps you to understand what we did if you got lost in it. I divided everything by 4 to simplify it down. Okay, then what I did is, where does the square root? I came back up here. Let me just tilt that up a little bit. And I solved for y in the black one, okay, because I was at an impasse. I had one equation with 2 unknowns. I needed to come back up to my other equation again. All right, so then what I did, now I'm sure there is another way to do this, but this is the way I did it, okay? I did it a different way the last time myself. I just don't know the way I did it before. All right, so there are different approaches to this. I got the same answer. Okay, so I solved for y, so I got x squared over to the other side by subtracting it. Then I took the square root to solve for y, okay? Plugged it in, back down here. So you see, if y was equal to this, and there's 2 here, 2 of them, then I have 2 of those, okay? I subtracted 6x on both sides. I squared everything. The 2 got squared. This squared gave me 64 minus x squared. This binomial squared gives me this expansion. That's where another point where students got uncomfortable, like, oh, really, we're dealing with these numbers? No problem when you have a calculator. We simplified this by distributing. Okay, then we got everything over and joined it up with the right, because now we have like terms over there, and now we have our quadratic, and we're all of a sudden feeling rewarded because now we're in a comfort zone again, and we can plug it into our quadratic formula here in purple, simplify that down to 2 situations, a plus or a minus situation. For one of the x's, and the other x, we plug back in up here, and we get our y's, and we checked to see if they were reasonable, and they were. All right?
Mr. Rosenthal, if you only want to deal with 2 equations at a time, another way to find the central point would be to find where A and B intersect, where B and O intersect, and where A and O intersect, and find the common point out of all 6 of those.
Assuming that they all intersect at a common point.
Assuming that they intersect at a common point, yes.
In the cell phone example, you don't know that. It's not the earthquake seismograph problem.
Well, in that case, you need to know the equations in order to find out.
Yes. All right, good. All right, so now you guys had a nice, deep, thorough experience with that. Now okay, let me give you the homework, and then I'm going to give you a challenge problem before we start the next lesson.
Already did the homework.
Thank you for sharing.
We didn't
You're
need to
welcome.
know that.
Yes, you did.
No, I didn't, David.
It's relative. For David, David required that you knew it. For you, from your perspective, from a different observation point, you didn't.
Not just my perspective, Mr. Rosenthal, the entire class's perspective.
Minus David.
Minus David, yes.
And that's speculation.
From my perspective, it disrupts the lesson.
Thank you.
Okay. Does it though?
Yes.
Okay. I think
Not to be mean, of course.
I think the jesting adds a little fun to the lesson. How about that? I think you're actually enjoying the jesting as well as I am. Let's have a little talk, you and me. Oh, you must have been saying that to, oh, it shouldn't be to everyone. It should be host. I keep doing other meetings where I want people to speak to everybody. Now I want it host only. Yeah, everybody's gonna try to get in their last words here. There we go, host only. There we go. All right. Put your archaeology hat on. You are an archaeologist. You're on a dig. And you found something from maybe ancient Egypt or Greece or something like that. This is what you found. Oops. A broken piece of plate. I want you to think about, now you're going to try to restore this plate to its original size and shape and everything. And how would you be able to find out the actual radius and the size of this plate, the real size of it? What would you
Well,
do?
if you wanted to find the exact radius, I guess you could measure the, well, in that case, it would make it shorter, but you could measure the length of the arc and its angle measure and use that to find the circumference.
You don't know its angle measure.
Well, doesn't it form an angle at the central point in the plate?
We don't know where the central point is. The central point could have broken off somewhere.
Well, in that case, then you could, you would have to,
I think Sun was right. You just find. Oh no, never mind.
Wouldn't you be able to find though the measure of the arc?
Well, let's say that you did. But look, you could have a little circle here and a big circle, and you could have the same, you could find the same measure here as here, right? They could both be 125 degrees.
or it could be a point outside the circle and it would intercept the arc exactly, wouldn't it? If you had a point outside the circle, the angle would need to be the same measure, right? I believe that was it.
Well, look, different size circles can have the same degree arc.
Oh.
You're going to need some lengths here. You don't have any lengths to go
We
with.
can measure the length of the arc.
Measure the length of the arc.
Yes. Also, we can put a point outside the circle and draw lines that are tangent to the plate at both endpoints of the arc.
Wait a minute. How would you measure the degrees of that arc if you don't know where the center of the circle is?
The length.
So you're saying then, how would you get the length? Okay, so you can maybe measure,
ruler.
take a string, lay the string out, and then pull the string out and measure it. Sure.
Yeah.
Let's say that you could measure the length of it. I don't know how, if you could explain to me how you would measure the degrees of that arc.
I would do this.
Without knowing where the center is.
I would,
because if the center is here, then the central angle is one angle. If it's here, then the central angle is a different angle.
Yeah, I'm explaining that. What I would do is I would put a point outside the circle and draw lines tangent to the plate at both endpoints of the arc.
Like that?
Yeah. And now I can measure that angle formed by the tangents.
Hey, that's what I said.
180.
That's not the full arc, because the full arc is from there to there and there to there. That's not going to meet those.
He says
Okay.
the endpoints of the arc.
But whatever arc we use, I'm gonna measure
He said
the
to
length
make.
of that
He
arc.
said to make the
I
tangent
just
to
make
those
the
endpoints,
endpoint.
not just to the arc.
They said that it's a theorem, right? That the measure of the angle formed by the tangents would be.
Oh,
the
you're
difference
okay. So
between-
draw a tangent from the endpoint here.
Yes.
Okay, and then draw a tangent from the endpoint there.
Yes.
And
And
then-
then measure that angle and subtract it from 180.
That's still what I said.
Okay, and so then you get
But
the.
I put it into words first, so there's some.
Okay, so now you have the measure of the arc, and then you have the measure. You have the measure of the arc and the length of the arc. Now, can you know what the full circle is?
Yeah, we can find the circumference and the
How
radius.
would you do that if you know the length? Let's say that this was 6 inches. This length of the arc. Okay, we'll call it AB. Arc length of arc AB. And let's say that that represented, let's make it easy on ourselves. Let's say that it represented 120 degrees is the measure of the arc.
The whole circumference is 18 degrees, and then divide by pi and 2. Divide by 2 pi and get the radius.
This tells you what fraction of the circle that is. That's a third of the circle.
Yes.
That length is a third of the circumference.
So the full circle is 18 inches in circumference.
Now that you have the circumference,
Divided by 2 pi.
yeah. But how would you locate the center?
Draw. Wait.
Now you're trying to recreate this. You could just make a circle that is 18 inches in.
How did you get 18
Circumference,
inches?
right?
How did you get 18
We multiplied by
inches?
3.
This is 120 degrees is a third of the circle, right? So
Yes.
if that length is also 6 inches, and that's a third, then triple that to get the whole circumference.
Oh, I see.
18 divided by pi is equal to the diameter, and then you divide that by 2.
That's what I was going to
Yes,
say.
we
Yes.
know, but we're trying to find the center. And we don't have the full plate. We can't draw all the radii from all the points on the circle.
You could just pick one point and draw a radius from that point, and that would allow you to extrapolate the location of the center.
But we don't know which way the radius should go.
What about the beginning of the chapter? Didn't we do this at the beginning?
if you know what a circle is, you
We did something at the beginning of the chapter that you should try to pull out here of how to locate the center of a circle using chords.
Perpendicular bisector of a chord intersects the center.
So you could make a random chord like that and construct the perpendicular bisector. And you know that,
And then measure 18 inches.
that line,
9 over pi.
that line contains the center of the circle.
Then measure 9 over pi inches from the outside.
Wait, how did you guys did you guys just assume that it was 18 or?
Yeah.
Actually, I made up some numbers. I said these are measurable things. You can measure by using our trick with tangents. You could measure the arc degrees. And then with a string, you can put a string from one point to the other and then take your string and lay it out flat and then measure that length. So you can get the length and the angle. If you could do that, and then I threw out some random numbers, you could then find the circumference, and then you could find the radius. Now they're saying if you know the radius and you know that it has to lie somewhere along this pathway, you could start at where it touches the circle and just measure 9 over pi.
It's not perpendicular.
Which is just under 3 inches in, and you'll find the center. That's one way to do it. What if I made another chord from, let's say, here to there, and I constructed the perpendicular bisector of that chord?
Oh yeah, what if you find the intersection between two?
Then that has to contain the center, and if both of the center must lie on both the blue and the purple, then you found the center right there. Okay? There were other methods. If I know the center, right? If I now find the center and now I can then find the length of the radius, I now know where that is. I can measure that. I could do that Wankel engine problem, right? Where this is x, right? And then if I completed an imaginary circle, I know this radius along this line was that measure of that radius, right? And then this would be 180. This would be the radius. Whatever the radius is, minus x would be this portion, right? This one is bisected, so you know that and you know that. And that would have been another way of finding these lengths. Okay? All right, so there's all sorts of stuff that we learned in this chapter, different ways to do it. I was going to show you this purple way with the blue and the purple, but you guys used other stuff, and you did exactly, to me, seemed reasonable way to approach the problem. Okay? Any questions about that? That was for fun. I just threw that in, the archaeology one. That's that problem I said last week. I was trying to find that problem in the book. I saw this problem somewhere, and I cannot remember, and I could not find it in the old book or any book. So I have no idea where I saw the problem. Maybe it was in a different edition somehow of the purple. I don't know. It's really strange to me. Could not find it. But it had something to do with this, trying to recreate that plate with the broken pieces to it. Okay, any questions? No? Okay. Then we can either start the next lesson or I can go into an early office hours, and we could just save this next lesson for tomorrow, which is the final lesson.
Early office hours.
Save, please save.
Yeah, let's save it for tomorrow. We can go into early office hours. So I'll see you all tomorrow. Dismissed.
Thank you,
Thank
Mr.
you,
Rosenthal.
Matt.
You got it.
Thank you, Mr. Rosenthal.
Goodbye. Okay, any questions now? I'm on office hours.
None. Thank you, Mr. Rosenthal. Have a good day. See you tomorrow.
You betcha, don't you know?
Bye.
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 bit early, huh?
Bye. Yeah, a little early today. Don't want to mix the ideas yet. Tomorrow's the last lesson of the book.
Okay. That means we get no more homework after that lesson.
That's not true.
No.
I'll have to upload the homework so that you guys can all access it.
Okay.
I have Cam Scanner now, so that's helpful. Anybody sticking around for questions? If not, I'm going to go ahead and end the session. Anybody have any questions for me? No? Okay. Nate, are you still there? Just an attendance check there. Nate, are you here? You could type it in. We could see your response if you're there. No? Ryan, Ian, Andrew, Adrian, do you have questions for me? Bye, Lauren. Well, she already checked out. No? Okay. Adrian, Ian? No? Okay, I'm going to end it.